Good day everyone, my name is Kimberly Carion and we are from Vet Electronics 3A and we are presenting to you our laboratory experiment in computer application course subject which is entitled the audio compression using wavelets through the MATLAB application. So here we can see our MATLAB application and we have finished the code needed to perform the laboratory experiment and it is saved in the program files in order to link it to the MATLAB software, and we will gonna be trying to run this here. So let's click add to path, and in here in the command window we see the my DCT, which is the created folder, a link to the MATLAB software, which stands for a discrete cosine transform, and there's an error meaning audio right, but figures have successfully appeared, meaning that it has successfully uh, transformed our codes into a GUI interface. So here we have figure 1, figure 2, and figure 3. We have an original waveform, which is written here in our code, the funky, and we have 3 compressed files from that audio original or initial audio format. We have named it compression factor 2 for funky 2, compression factor 4 for funky 4, and compression factor 8 for funky 8. This means that we have 50%, 75% for factor 4, and 87.5% for factor 8. So here in our simulation, an audio waveform was highlighted as a continuous sequence of data in one long vector. In that sense, an audio data structure is different from an image data structure because an image can be visibly seen but an audio can be heard. And next, the technologist needs to apportion the vector manually into several pieces and cannot rely on existing rows or columns. First that we have done here in the simulation is that we read the audio file, the initial audio file, which is placed here in our desktop, mainly on our DCT folder, which I have said earlier, and this funky music or audio file is our initial or our original waveform, which has a property, a size of 732 kilobytes, approximately 750 by 260 bytes. So first we read this file inserted in our code. And second, we determine the value for number of samples that will undergo the discrete cosine transform principle at once, meaning the audio vector will be divided into pieces of this length, which is what we have seen in these figures. Observing this, we can determine the different sizes of waveforms that they have accumulated from the original waveform to the last compressed file. So next, and again, the technology examine the different compression rates. So we have the 50% for 50% for 2, and 75% for 4, and 87.5% for the compression factor 8. And lastly, it results to compressed and uncompressed audio waves. So the uncompressed waves is the original waveform and the others are the compressed waveform. So in simple manner, the technologies iterate over the vector, window by window, but let us disregard whatever remainder exists. So in the figure 1, The technology is able to plot the time domain and, moreover, closer inspection does not reveal qualitative differences in the densely packed regions or the high frequencies here. And observing the spectrogram, which is in the figure 3, reveals a clear idea of the loss of high frequencies. Look at this. The original waveform, the original audio format, has high frequency. Meanwhile, as we observe on the 50%, 75%, and 87.5%, it decreasing in terms of frequency. And the qualitative difference is clearly apparent when listening to the audio files. After discussing all these figures, we will now proceed to listening the differences between the funky initial music to the remaining compressed audio files. So saving the files and viewing the difference in size will be done later. So let us discuss deeper. So audio noise reduction is the system that is used to remove the noise from the audio signals. Audio noise reduction systems can be divided into two basic approaches. The first one is the complementary type, which involves compressing the audio signal in some well-defined manner before it is located. And the second approach is the single-ended or the non-complementary type, which utilizes techniques to reduce the noise level already present in the source material. Audio compression is a very good example of speech and signal processing. People use internet for various purposes and entertainment. And audio is common in all entertainment applications. So if an audio file is large, it takes more space to store, and we know that in this technological era and in this new normal, we need more space, more RAM, more memories, more hard disk, more flash drive to store our files. So with this audio compression, we can, even in this little manner, we can save space so that we can save more files into our flash drive, hard disk, RAM, or anything where we store our storage. So, an audio sample named Funky, which is discussed earlier, here is taken and analyzed to our program, to our coding, using our MATLAB software in determining the frequency and amplitude. The discrete cosine transform principle is applied on the audio as it was being compressed. So we used the discrete cosine transform principle here, and the audio sizes before and after compressions are compared. So here are the figures that shows the differences of in terms of frequency and amplitude. It is really observable here, right? And then there are some parameters that we have used to program the compression. So we use as the Debonche's wavelet transform to perform the following function. First, we select an audio and finds the actual signal size. So we have determined the size earlier using the property section. And then, second, we determine the amplitude and the frequency. And in our figures, we have frequency and time. And then, second and third, we choose a block size. So we know that frequency is okay. Let's move on. So first, we change the compression percentage, and fifth, we initialize the compressed matrix. And lastly, and it works on the compression using the discrete cosine function, which we have used. And it will eventually rewrite the signal and lastly look for the size of compressed signal. So let us hear. This is the original audio format. So the original audio format shows high pitch sound and it's relatively high in size. So let's look to the other compressed file that we have processed using this MATLAB simulation. Let's look at this funky tube. For that, let us determine its characteristic or the properties in terms of size. We have accumulated 720 kilobytes or approximately 737.324 bytes, which is relatively different to our first original size, which is 732 kilobytes or approximately 750.260 bytes. So there's difference, even if it is small. So let us hear the funky. So while hearing this compressed audio, we can determine that it really changed, it really compressed. And look at this compression factor too. It has slight difference from the original waveform, but looking in this figure 2, it shows a slight difference from the first one. But looking at the frequency and time domain, we can see that it decreased in terms of frequency from the original waveform. That's why we can hear that it changed its sound quality to low, and it's like it's turning the high pitch to bass sound. Next, let's look at this funky 4 and determine its properties in terms of size. So it has 720 kilobytes or 737.324 bytes, which is the same to our funky 2 but relatively different to our original audio format size. So let's hear it. So hearing this third compressed audio signal, it is really different from the first. Basing on the technical aspects, we will observe the graph that we have accumulated based on our MATLAB coding. So this is a compression factor 4, and it's still decreasing in frequency compared to the compression factor 2. So it becomes relatively slower than the second one, and uh, had a huge difference with the original waveform. As well as in the figure 2, you can clearly see the difference in terms of portion of the original waveform. And here it is compressing. And for our last compressed audio file, we will hear the funky 8 with property in terms of size 720 or 737.324 bytes, which is the same on our previous compressed format, which is the funky 4. So let's hear it. We have heard the last compressed audio format. We can determine the difference from the original to the from the 87.5% compressed audio format, which has approximately this is 0.1 with a 0.1 frequency. Using time domain and looking at this portion, it relatively became thinner compared to our original waveform. And under figure 1, it compressed. It has a great difference from our original waveform. And with all this accumulated stuff, let us conclude. So we have used the principle of discrete cosine transform here in our simulation for today, which then a discrete cosine transform highlights that it is a lossy technique that removes certain frequencies from the audio data such that size is reduced with reasonable quality. So a discrete cosine transform is a first-level approximation to MPEG audio compression, which are more sophisticated forms of basic principle of discrete cosine transform. So it takes a wave file as an input and compresses it to different levels and assess the output that is compressed in each wave file. The difference in the frequency spectra will be viewed to assess how different levels of compression affects the audio signal. So we can also define that an amplitude is the strength of wave's effect. So the higher the amplitude, the more air molecule is displaced. And let us define waveform. Waveform describes wave by graphing how air molecules is displayed over time. So it is the frequency and time domain. So we can see different waveforms here. which describes the way by graphing how air molecules is displaced over time. And the audio wave is the vibration of air molecules, which how sound travels. So the audio compression is the elaborative guide in compressing audio file format for a specific embedded sound audio. So that's all, everybody. Thank you for taking time on listening on our laboratory experiment, and I hope you have learned so much, and may God bless you all. Take care for adieu. See you guys.